Before going into the more mathematical aspects of finite element method, we are going to start with a very simple problem. My purpose for doing this is that the simple problem will help me explain to you all the operational aspects of the finite element method, how a finite element code works. So this is the problem of a 2D planar truss, and um, the first step in a finite element analysis is to divide the problem into suitable elements and nodes. And in this case, these are our elements. So this is an element number, it has been numbered as 1. This is another element, it has been numbered 2, and so on. There are 7 elements. Wherever the elements are joined, these points have also been numbered from 1 to 4, and these points are called nodes. So uh, the elements and the nodes constitute the whole system, which is the mesh. The mesh is also, the truss is also supported by a hinge at this node and by a roller at this node. There are also two forces. There's a global XY coordinate system. So all the solutions that we want are to be in this global coordinate system. Now you must note this is a planar truss. So any node, for example, this one can move either in the X direction or in the Y direction. So this node we say has 2 degrees of freedom. So we have 2 degrees of freedom per node. Right now all nodes have exactly 2 degrees of freedom. All the nodes have the same number of degrees of freedom, but we can also have problems where some nodes have larger number of degrees of freedom than others. But for the time being, we will consider problems where all nodes in the mesh have uh, exactly the same number of degrees of freedom. In this case, there are 2 degrees of freedom per node. Also, all the forces that you have, these are external forces that we have applied, are applied in the global xy direction, and they are applied at the nodes. There are no forces applied, for example, in the middle of an element. We are not looking at that situation yet. So for these elements, which we will call truss elements, so each of these elements are truss elements, and all the elements in this mesh are truss elements. We will see what truss elements are in a moment. So for this mesh constituting of truss elements, we will apply forces, external forces, only at the nodes, and that is what we have done. So F1 and F2 are the forces applied at node 5. Again, completely arbitrary. It could have been applied anywhere else, but the point is that the forces have to be applied at the nodes. So there are 7 elements in this structure. All elements are truss elements. There are 5 nodes, and each of those nodes has 2 degrees of freedom. So the numbering of the nodes and the numbering of the elements is completely arbitrary at the moment. So we have just numbered it in some way, whatever came to our mind. But we will see that a better numbering system can be devised based on what we are going to learn very soon. So with this mesh consisting of truss elements only, I am going to demonstrate to you all the major steps that are there in a finite element procedure. Let us start by taking one single element out of this and drawing its free body diagram. Let us take this element out. We could have taken any other. Let's take this element out. So when you take this element out, this is your element number 4, and then this is connected to 2 nodes which are labeled 4 and 2. So in a finite element code, the input to a finite element code would be these connectivity tables. So the connectivity table will say, for example, no element 1 is connected to nodes 1 and 5. So element 1 is connected to 1 and 5. Element 2 element 2 is connected to, let's say, 5 and 2. Element 3 is connected to 1 and 2. Element 4 is connected to 2 and 4. Oops. Element 4 is connected to 2 and 4, and so on and so forth. So for every element you will have what is known as a connectivity table. So this is a connectivity table for this mesh. So connectivity table tells you that element number E has nodes n1, n2, n3 connected to it, or n1, n2, n3, n4, depending on the kind of element you have. In this case, we have two nodes per element. We have truss elements which have two nodes per element, and therefore your connectivity table will say that any element number E, where E goes from 1 to 7 in our case, is connected to n1 and n2, two nodes. Okay, now other thing that we need to define this structure are the coordinates of the nodes. So we need the nodal coordinates. So to get, so that also has to be specified to the user, by the user. So that would take some form like node 1 has x coordinate of 0, y coordinate of 0. Node 2, which is the node here, node 2 has, let's say, x coordinate of 1 and y coordinate of 0. Node 3, which is this, has, let's say, x coordinate of 2, y coordinate of 0. Node 4 has again what, 1.5, 1.5 is x, and y is maybe 1, and so on and so forth. So these are nodal coordinates. So this goes by number of nodes in the whole mesh, and for each node you have to specify the nodal coordinates. Now once the nodal coordinates are given, so you give the nodal coordinates, you give the connectivity table. Once these two things are given properly to your finite element code, the geometry of your mesh is completely defined. So we have specified all the nodal coordinates of the 5 nodes, and we have told for each of the 7 elements, we have told which nodes are connected to that particular element. Once these two information are passed on to the code, then the whole geometry is defined. Apart from this, the user also has to tell the code in some manner uh, 3 more things. One is, what are the material properties of this, of each of these elements? Are they made of the same material, or they have different material properties? In this course, we are going to do only linear problems, so we will be interested only in um, linear elastic material properties. For an isotropic system, isotropic linear elastic system, you need only 2 properties. So you need only E and nu for an isotropic elastic material. So you have to specify E and nu for each and every element in your mesh. In case of a truss, we will see that the only property for each element that we need is E times the cross-sectional area of the truss. So once we give E times A for each element, all the property definition is complete. The property definition is complete, and you need nothing else. So it is the number of properties, that property parameters that you have to give for elastic problems are generally small. But for more complicated problems, nonlinear materials, you might have to give a lot of property parameters. For our cases, for elastic materials, we will generally give only E and nu for each and every element. Um, and for trusses, and we will later do beams and so on, we will have to give even smaller number of property parameters. And for the truss, it's the value of E times A. So you have to give E times A for element 1, for element 2, element 3, element 4, and so on. That's one additional information that you need. The other additional information that you have to supply to your finite element code are the external forces that are applied. So as I said, in this problem and in many other problems that we do, that we are going to do with structural elements. So these are structural elements, these are truss, beam, etc. are um, are things that you study in your strength of materials course, and these are called structural elements. They are slightly different in spirit from solid elements that we are going to learn about later, with which you mesh complete, say, a half space or a complete solid object. So those solid elements are slightly different in spirit from the structural elements like beams, plates, shells, trusses, and so on. So these for these structural elements, many a time we will apply forces at the nodes. So for every node, you will have to tell the finite element code whether there are any external forces applied. So here no node has any external force applied except uh, node number 5, where there are two external forces, F1 and F2, minus F1 and F2, applied in the X and Y directions. So we have to pass that information to the program in some way. The last information that the program also needs is about the boundary conditions. So here node numbers 1 has a hinge, which means that it can neither move in the x direction nor move in the y direction. So both the degrees of freedom at node number 1 are fixed. Whereas at node number 3, it cannot move in the y direction. This is a roller. It cannot move in the y direction but can slide in the x direction. So only 1 degree of freedom is fixed, and the fixed value of the 2 degrees of freedom of 1 and 1 degree of freedom of 3 are all equal to 0. So the displacements that these nodes can have, in the x direction as well as in the y direction are specified to be 0. And in this, the displacement it can have in the y direction is specified to be 0. So let us just enumerate what are the information that the user has to input to a finite element code in general. And these are firstly nodal coordinates, then element connectivities, material properties associated with every element, boundary conditions, and external force. So these are the essential informations that will be needed to run this problem and give you a solution. The computer gives you a solution. So this much of information will definitely be needed. There may be other kinds of information wanted from you, but those are not essential information. Those may be information about what you want to output from the code and so on. But this is the essential information, and we will see one by one how this information is going to be used. Okay, so let's see that in the next lecture.